So today we're going to be doing example 5.2, which is on cycloid motion. The example says, a more exotic trajectory occurs if we include a uniform electric field that is at right angles to the magnetic one. Suppose, for instance, that the magnetic field points in the x direction and the electric field in the z direction. As shown in figure 5.7, a positive charge is released from the origin. What path will it follow? So figure 5.7 pretty clearly depicts the path that this charge is going to follow, but let's talk about why. First, to review, the Lorentz force is given by Q times the electric field plus the cross product of the velocity and the magnetic field. Now at t equals 0, when this system, right at the beginning, this charge is not moving, so the velocity is 0, so the only force it feels is due to the electric field, which is pointing in the z direction. So at t equals 0, F equals QE z hat. Now when this happens, the charge is going to start accelerating in the z direction, and so, because it has a velocity, it is going to feel a magnetic force. Now, the velocity is going to be in the z direction, and as previously mentioned, the magnetic field is going to be in the x direction. So, then the full form of the Lorentz force is going to be F equals Q E Z plus V Z cross, not plus, cross bx. So this term right here is going to create a magnetic force in the y hat direction, which is why you see that essentially what happens is this charge begins by accelerating in the z direction, and that develops the force in the y direction, which pulls it over and towards the y-axis until it comes down. And at this point, it's opposing the electric force pointing in the positive z direction, which is why it kind of stops, and then the cycle repeats itself. So now we can go about this a little more quantitatively. So we know that in this case, the motion is only in the yz plane. It's not moving in the x direction. So at any point, the velocity is going to be v equals none in the x direction, y dot, that's just the time derivative of the y position, z dot. So then we can say the v cross b is equal to z hat which will give us, okay, so in the x direction, it'll be 0 minus 0 in the x hat direction, minus 0 minus b z dot in the y hat direction, plus 0 minus b y dot in the z hat direction. So this simplifies to b z dot y hat minus b y dot z hat. So then the entire Lorentz force, which we have written up here, becomes F equals Q times the electric field, which is in the z hat direction, plus b z dot y hat direction minus b y dot in the z hat direction. And this, of course, as I may have mentioned, F equals ma, and the motion is constricted, or not constricted, but it is, I guess, yeah, it is constricted to the YZ plane. So we can say that this is equal to m times y 2 dot y hat plus z 2 dot z hat, because it's accelerating in some way in the YZ plane. So then from here we can go ahead and isolate the y and z components, and essentially we end up finding QB z dot is equal to, and these dots, to clarify, are time derivatives. So of course this is the velocity in the z direction, that's the first time derivative. This is the acceleration in the y direction, that's the second time derivative. So yeah. And QE minus QBY dot is equal to MZ 2 dots. Okay, so then we can go ahead and we want to isolate the second derivatives. So we'll get y 2 dot equals QB over M z dot, and z 2 dots equals QE over M minus QB over M y hat. So now we can go ahead and define the cyclotron frequency. So omega is equal to QB over M, which we've covered in advanced classical mechanics. So then this becomes y 2 dot equal to yeah, I'll just keep it out. I'll just keep it like this for now because I'm gonna reduce this one. Z 2 dots can be written as QB over M times E over B minus y dot, where this is the cyclotron frequency. So then the general solutions to these differential equations, actually, yeah, I'll go ahead and rewrite them. The general solutions to these are 5t equals to c1 cosine omega t plus c2 sine omega t plus e over b times t plus c3. And that's for the motion in the y direction, and then for the motion in the z direction, c of t is equal to c2 cosine omega t minus c1 sine omega t plus c4. So yeah, these are the two general equations. Now we know we're going to have to solve for the constants, so the question is, what are our boundary conditions? At the very beginning I mentioned that at time equals 0 that charge is not moving. Its position is at the origin and it's not moving. So that gives us our boundary conditions. We'll say boundary condition 1 is that at time equals 0, so y of 0 is going to be equal to z of 0. It's just equal to 0 because at the beginning it's in the origin. Our second boundary condition, or second set of boundary conditions, is going to be that at time t equals 0, the velocity is also equals 0. So y prime of 0 is equal to z prime 0 is equal to 0. So boom, then we have our two boundary conditions. But this also means that we need to find the time derivatives of our, essentially the time derivatives of our position functions. So the time derivative of our position in the y is going to be equal to minus c1 omega sine omega t plus c2 omega cosine omega t plus e over b. And then for the time derivative of the z position, it's going to be equal to minus c2 omega sine omega t minus c1 omega cosine omega t. Okay, so when we plug in the boundary conditions, I mean, you're essentially just going to be plugging in zeros. So, just for ease, I'm not going to write out sine of 0, cosine of 0. Those are just going to be 1s and 0s. So, following boundary condition 1, or the set of boundary conditions, the first set of boundary conditions, y of 0 is going to reduce to c1 plus 0 plus 0 plus c3, which is equal to 0. C of 0 is equal to c2 plus 0 plus c4, which is equal to 0. Now y prime is going to become 0 plus omega c2 plus e over b, which equals 0. And here it's with the time derivatives that you can actually start solving for these constants. So from here we can go ahead and say c2 is going to be equal to minus e over omega b. Now for the time derivative of the z is going to go to just minus c1 omega is equal to 0. So this is great. We can say that c1 is equal to 0. Now if we go back to the top, c1 plus c3 is 0. If c1 is 0, then c3 has to be 0. And based on the second one, c2 plus c4 equals 0. So therefore, c4 equals e over omega b. Sweet. So now we can go ahead and rewrite our general equations with these constants. So our motion in the y direction is going to be to minus e over omega b sine of omega t plus e over b times t. We want to put everything in terms of omega t, so I'm going to factor out this term here, the e over omega b, and then multiply this term by omega, and that'll keep everything the same. So that would then become E over omega b times omega t minus sine of omega t. Oh, actually, a good little reminder that tripped me up earlier is when you're taking the time derivatives, always remember your chain rule, and that's why you pull this omega out front. Okay, back down here. Because if you don't do that, then this section won't work. Okay. So now for z, will be equal to minus e over omega b cosine omega t plus e over omega b, which you can factor out the e over omega b. One minus cosine omega t. Cool. So now we can call, what do I want to, yeah. We'll call this term e over omega b, we'll call this r. And the reason for that is because this, I mean, as shown in figure 5.7, it is rotating in its semicircular motion, so that motion is going to have some radius r. So we'll call that r, and then these equations become y of t equals r omega t minus r sine omega t, and z of t is equal to r minus r cosine omega t. So now we can leverage, using these two equations, we can leverage the fact that, of course, sine squared omega t plus cosine squared omega t is equal to 1 by essentially accounting for these terms like this. So we can then say y of t minus r omega t, quantity squared. So that minus r omega t deals with that, the r omega t there, plus z of t minus r, quantity squared, is equal to r squared. And look at that. This is the equation for a circle, and this is a circle of radius r. Circle of radius r centered at zero, r omega t, r. So as you can see, the center of this circle, the center of this circle up here, is going to be moving with time along the y-axis, which is why we have that there. Then, so it's traveling in the y direction at a constant speed. And then we can also say, because we have this, as we said, r is equal to e over omega b, we can then say that the, the tangential velocity of, if you have that circle, your tangential velocity, recall, is v equal to r omega. We're basically going to do the same thing here. So in this case, we'll call it U and say that is equal to R omega, which is equal to E over B. Yes. So essentially what's going on is that this is moving like a spot on a wheel which is rolling along the y-axis. So we'll come back to 5.7. This is going to be moving along this wheel and then stop, and then speed up, and then stop, and then speed up and slow down. And it's just like if you draw a dot on a bike wheel and you are watching that, that is what the motion is going to look like. Anyway, thank you so much.